The digital computer, though it lacks imagination and initiative, does have certain human-type capabilities. It can read instructions and data. It can retain what it reads. It can execute instructions. It can calculate data and make simple decisions. And it can write its solutions to problems. These functions are performed by the 5 major units of the computer. Input is designed to read, storage to retain, control to execute, arithmetic to calculate, and output to write. It is our purpose in this film to in each of these, seeing the type of equipment used and its function. The input and output units are called peripheral equipment because they are on the outer edge, as it were, of the computer. They may be considered the links between the problem, the computer, and the solution. In a sense, this is so, but we must remember that an input medium and an output medium are necessary parts of the overall system. They are apt to be confused with the computer input and output units, but the distinction should be clear. The computer input serves to read the problem information carried by the input medium and translate it into electrical pulses for storage. Conversely, the computer output serves to write information, translating the output electrical pulses into output medium form, cards, tape, or printed paper. When the computer input reads the input medium information, the decimal numbers and other data are encoded into binary digits. One type of encoder is a rather simple circuit of 4 OR gates, with the input designed to receive the decimal numerals, one at a time. Each is converted to a 4-bit binary combination which can be stored. 2, for example, is encoded as 0010. 7 comes through this way. 0 input does not have to go through the gates. The output will be 0000 when there is 0 input. The problem information, instructions and data, is carried by the input medium. Punched cards, punched paper tape, and magnetic tape are the usual forms of the input medium, with a manual keyboard as an input device that may also supply information if necessary. The keyboard is used principally for checking the computer operation at various points in the processing of a problem, and for making special insertions, such as new data or revised instructions. The speed, of course, is slow, only a few digits or letters per second. Card reading devices can absorb the data at rates of many thousand bits per second. These may be fed direct to the computer input, known as online operation of the reader, or the data may be transferred onto tape for faster input to the computer. Incidentally, the first use of punched cards in industry was in the year 1800 for programming the weaving of patterns in rugs and carpets. Punched paper tape, too, can be read into the computer at high rates. The first use of punched tape was to accumulate telegraph signals for rapid transmission, invented by Samuel F.B. Morse himself over 100 years ago. Magnetic tape has enormous capacity and operates at very high speed. One reel can carry the data punched into 33,000 cards and can put over 500,000 bits per second into the computer. At that, it cannot usually come up to the rate at which the computer processes the data. This means that input reading rate and output writing rate may, in some instances, control the overall speed of the system. For this reason, magnetic tape is also used as the output medium, to extract the solution as quickly as possible. When speed is not so important, the output may punch the data into cards or paper tape. The electric typewriter used for input may also be used to print out the solution in human language. Its best speed, however, is about 15 characters per second, which is far too slow for voluminous data. High-speed printers have been developed for use with computers and output media. In this one, the numerals and other characters are on a moving chain. Another design uses wheels to carry the type. The wheels rotate to place the characters in position for printing. Another system prints by means of dots that originate within a matrix device. Each character is printed by wires made to project from a matrix block, each wire being controlled by a magnet. Any letter, number, sign, or symbol can be presented and easily read. Input and output devices are constantly undergoing study and development to increase their speed. Continuing research will result in further advances in the state of the art. Now let us turn to the storage unit, whose function, as we know, is to file data and instructions for use in processing. Symbolically, it resembles the array of mail and message boxes behind the desk of a hotel. Each cell is identified by a number called its address, such as 304, for example. This represents a small section of a storage unit, which actually may contain thousands of cells. Certain sections of the storage unit may be designated as registers for intermediate storage of data in process and other special uses. Instructions may be stored in consecutive addresses so that when each instruction has been executed, the advance to the next instruction can be made automatically by raising the address number one count. Data are usually stored in separate groups of addresses apart from the instructions to avoid mix-ups and programming errors. Data are transferred into and out of storage as words containing 10 to 40 or more characters or bits. The operation to be performed is given by a code number, meaning add, subtract, or some other operation. Other parts of the word give the addresses of the data to be used in the operations. In virtually all computers, the storage cells are magnetized surfaces of various types. Magnetic tape may be used for storage, but it has the disadvantage of excessive access time. That is, the time required to get to a specific address may be unduly long. The time can be reduced by using many short tapes rather than one long one. The magnetic drum is a storage unit that may be considered as a cylinder with magnetic tapes wrapped around it. The drum is fitted with heads that read and write data while the drum is constantly rotated at speeds upward of 6,000 RPM. Thus, access time is very short, since each cell or bit location speeds past the heads many times per second. Magnetic disks are also used for storage. Each side may have up to 100 tracks or channels in which data are stored, and both sides are equally accessible. Disks are stacked to form a storage unit and are kept rotating continuously. The read and write heads are moved to the designated tracks in a few tenths of a second, thus providing excellent access time. Since the access time is virtually the same for all addresses, they can be selected at random, which gives this type of storage its name, random access. In contrast to moving or dynamic types of storage units, computers may use static types. The outstanding one is the magnetic core matrix. It consists of small rings or cores made of ferromagnetic material strung on a network of wires. To see how each core operates, let's first thread a wire through one of them. The core's ability to store data is based on the fact that a pulse of current will magnetize the core to saturation, the polarity depending on the direction of the current. Binary 1 can be associated with one polarity, and binary 0 with the opposite polarity. Thus, binary data can be stored in the core. It holds the 0 or 1 magnetization until a reverse pulse switches it. A sensing wire is used to read out the state the core is in, 0 or 1 at any given time. A pulse of current in this direction will now switch the core's polarity, and the change of magnetic flux induces an output voltage or signal in the sensing wire. With the core in the 0 state, another pulse in the same direction will not cause it to switch, because the 0 polarity is associated with this current. Therefore, there is no output signal. Thus, when the core is pulsed this way, the absence of an output signal indicates that 0 was stored. Conversely, the presence of an output signal indicates that 1 was stored. Incidentally, since a 1 bit is lost when the readout process switches the core to 0, it is usually restored by putting a pulse on the output wire. In a core matrix, 2 switching wires and a sensing wire are used with each core. Each switching wire is permitted to carry only half the current required to switch a core. To switch a particular core, 2 switching wires are pulsed simultaneously, and the combined half currents switch the polarity of the core. The other cores on the 2 pulsed wires are not switched, since only half currents go through them. Core matrix storage has the advantages of instantaneous access to all addresses, no moving parts, no wear, and consequently, a high order of reliability. Its incorporation in a specific computer depends on the performance requirements. Let's turn now to the arithmetic unit. Its function is to make the necessary calculations and logical decisions. To do this, the unit makes use of adding devices and other components. Some of these are half adders. They can add 2 binary digits, but are not designed to receive a carry. A half adder may be composed of an OR and 2 AND gates and an inverter. It receives 2 input bits and produces 1 or 2 outputs, the sum, and when present, the carry. We will use 0 for no pulse or low-level voltage, and 1 for a pulse or high-level voltage. To see how this half adder operates, let's first use 2 0 inputs. The 2 zeros at the first AND gate result in a 0 as its output, causing the carry output to be 0. This 0 output is applied to the inverter, and it becomes a 1 input to the AND gate. The 2 input zeros enter the OR gate, resulting in a 0 output, which is a 0 input to the AND gate. This 0 and the 1 result in a 0 output as the sum output. 0 plus 0 then equals 0, which is the correct result according to the rules for binary addition. A 0 and a 1 as inputs will put a 0 and a 1 into each of these gates. The AND gate output will thus be 0, which is then the carry output. the inverter changes the 0 to 1. At the OR gate, 0 and 1 produce a 1 output, which is the input to the AND gate. The output of this AND is therefore 1, and so is the sum output. Thus, 0 plus 1 equals 1, and the addition rule is observed. You might note that reversing the inputs would make no difference, since both of them enter both input gates. With both inputs 1s, there will be a 1 here and a carry 1 output. Because of the inverter, there is a 0 here. With 1s on the OR gate, there will be a 1 here and here. Therefore, the output here must be 0, resulting in a sum of 0. Thus, 1 plus 1 equals 0 plus a carry, that is, 1, 0, again conforming to the rule. For subtraction operations, which require complements of numbers, the half adder is used without its carry output. Complementing is inverting the bits. The number to be complemented is put in, along with a train of single pulses called the clock pulses of the computer. With 2 1s as inputs, the sum output is 0. This is the complement of the input digit. A 0 and a 1 entering together will result in a 1 output, the complement of the input. Thus, each bit is reversed as required. A half adder may also be used to show whether two numbers are identical. If the two input bits of a pulse interval are the same, either 0s or 1s, the sum output will be 0 by the rule. Therefore, as the words go through, a continuous sum output of 0s shows that the numbers are identical. If the inputs are not identical, 1s will appear in the output. This is how identity is determined by the arithmetic unit. In addition to half adders, the unit contains full adder circuits. A typical one may be composed of 2 half adders and an OR gate. The third input is used to accommodate a carry from a previous addition. The full adder handles any combination of input digits. The circuitry in the arithmetic unit appears to be complex, but it is actually made up of simple basic circuits. The components are standard types of diodes, capacitors, resistors, and so on. Now the control unit, the nerve center that makes the computer operate by automatically selecting instructions, interpreting them, and causing them to be executed. Time is a key factor in control, for sequencing, for clocking in millionths of a second, and for cycling. The cycling involves two operations, instruction and execution. These are performed alternately and continuously throughout the problem-solving process. Let's follow a typical cycle by means of a simplified flow diagram. In addition to the cycle switching device, the control unit contains an instruction location counter, an instruction register, a data address register, and an operation decoder. The arithmetic unit contains an accumulator, a register used for temporary storage of the results of computations. Let us assume that the storage unit contains 10-digit data and instruction words received from the input unit. and that the instruction location counter has been set to the address of the first instruction. When the computer is started and instruction time begins, the instruction location counter causes the instruction word to leave its storage address and be placed in the instruction register, where it remains during the processing. Such an instruction might be add contents of address 2478 to contents of address 1245 and store in accumulator. The operation part of the instruction is interpreted by decoding and then sent to the arithmetic unit, setting it up for the type of operation ordered, add in this case. The data address part of the instruction is placed in a register connected to storage. The instruction register then causes a switchover to execution time. This time begins with the transfer from storage of the data at the given addresses into the arithmetic unit. The computation is done, and the result is stored in the accumulator as instructed. During this time, the instruction register causes the instruction location counter to advance one count, so that it will contain the location of the next instruction word. When the operation is completed, the arithmetic unit causes switchover to instruction time. The entire cycle is now repeated, starting with the transfer of a new instruction out of storage. The instruction time is always the same for every cycle, since the instruction words are always the same length in a given computer. Execution time, however, varies according to the type of operation involved and may be long or short. The final instruction in the program calls for transferring the solution from the accumulator to the output. The control operation is, of course, much more complex than shown here. There are more components. Logical decisions may change instructions, and input and output are controlled. However, you have seen the basic procedure. Incidentally, the names of these components may vary from one computer system to another. The control unit circuitry, like that of the arithmetic unit, is made up of standard electronic components. If trouble develops in any unit, success in finding the source lies in an understanding of the logic design and the ability to interpret a logic diagram, rather than in trying to trace through circuit schematics. In this film, we have examined each of the 5 major units of a typical digital computer. We also saw how some of the computer operations are accomplished, and how operation is based on 2 processes, instruction and execution.